Welcome to Chapter 9. This chapter is the final part of diagnostic analytics. In this chapter, we will see what correlation and regression analysis are. These analyses are one of the most popular methods for diagnostic analytics. By the end of this chapter, you will be able to explain what correlation and regression analysis are, including their benefits and limitations. Explain the difference between correlation and regression analysis. Interpret the results of correlation and regression analysis. As the first section, let me talk about correlation analysis. It examines a linear relationship between two numerical variables. Recall that we can visualize the relationship between two numerical variables using a scatter plot. The scatter plot on the left shows a positive relationship clearly. And we can see a negative relationship in the scatter plot in the center. However, we cannot see clear relationship between x and y in the plot on the right. Sometimes we want a quantitative measure to evaluate the relationship between two numerical variables. In such a case, correlation coefficient is useful. Correlation refers to a linear relationship between two variables. If the two variables move in the same direction, those variables are said to be positively correlated. If the two variables move in the opposite direction, those variables are said to be negatively correlated. And because a correlation means a linear relationship, it can be approximated by a straight line. It is important to know that correlation refers to a linear relationship where two variables move in the same direction or the opposite direction. So, if we can approximate the relationship between x and y by a horizontal straight line, we should say there's no correlation. A straight line can approximate the relationship, but the two variables are not related in the same direction or opposite direction. In this case, y's values are the same even when x's values changes. It means that y's value is not related to x's value. So, in such a case, we should say that x and y are not correlated, or there's no correlation between x and y. It should be noted that no correlation does not mean there is no any relationship between two variables. Correlation quantifies a linear relationship only. It cannot quantify non-linear relationship. For instance, in this scatter plot, we can clearly see there's a U-shaped relationship between two variables. However, there's no correlation because there's no linear relationship between the two variables. Another point to be noted is that correlation does not imply causation. Correlation means that there's a linear relationship between two variables. The fact that two variables are correlated tells us nothing about their cause and effect relationship. Correlation analysis just tells us that the two variables are linearly related. So, we cannot identify which is the cause and which is the effect. To quantify the strength of correlation, we can use correlation coefficient. A correlation coefficient is a measure that quantifies the valence and the strength of the correlation. It is usually denoted as R. The correlation coefficient ranges from -1 to 1. The larger its absolute value is, the stronger the correlation is. The correlation strength means the degree to which the relationship between two variables can be approximated by a straight line. When the correlation coefficient is negative, the correlation between the variables is negative. When the correlation coefficient is positive, the correlation between the variables is positive. And the larger the absolute value of the correlation coefficient is, the stronger the correlation is. This figure summarizes the criteria for interpreting the value of a correlation coefficient. There is no consensus on the threshold of strong and moderate and weak and so on, but we can use these criteria as a guide. And as I noted, the correlation strength is the degree to which the relationship between two variables can be approximated by a straight line. Let's look at these scatter plots. In the left plot, the dots are widely dispersed from the approximation straight line. In the right plot, the dots are concentrated around the straight line. We can say that the relationship between the two variables is more linear in the right plot than in the left plot. So, the correlation is stronger in the right plot than in the left plot. So, the absolute value of the correlation coefficient is larger in the right plot than in the left plot. In these plots, as x increases, y also increases. In such a case, the approximation line is upward sloping. It represents a positive correlation, and the correlation coefficient is positive. When y decreases as an increase in x, the approximation line is downward sloping. It represents a negative correlation, and the correlation coefficient is negative. Let's see the scatter plots with correlation coefficients. In the upper three plots, the correlation coefficients are positive. And the more you go on to the right one, the larger the correlation coefficient is. And the more you go on to the right one, the more the dots are scattered along a straight line. So we can see that as the correlation coefficient approaches 1, the positive correlation gets stronger. That is, the data distribution approaches an upward sloping line. Next, let's look at these two scatter plots. These plots show negative correlations where the data points distribution can be approximated by downward sloping lines. And compared to the left plot, the center plot has a correlation coefficient with a larger absolute value, and the data points are more concentrated on a straight line. They show that as the correlation coefficient approaches -1, the negative correlation gets stronger. That is, the data distribution approaches a downward sloping line. Lastly, in the lower right plot, the correlation coefficient is positive, but its absolute value is small, -0.16. And as we can see, the data points seem to be randomly scattered. We can hardly see a linear relationship between x and y. So, we should say that there is no or a very weak correlation between x and y. We can compute a correlation coefficient by this formula. Detailed mathematical understanding is beyond the scope of this course, but let me give you a brief explanation. The numerator of this formula is called covariance, which represents the two variables' co-movement. If the two variables move together, the covariance is positive. And if the two variables move in the opposite direction, the covariance is negative. To compute the correlation coefficient between x and y, we divide the covariance between x and y by the product of x's standard deviation and that of y. If our dataset contains many numerical variables, A correlation matrix is useful to highlight the correlation between variables. Correlation matrix displays the correlation coefficients between pairs of variables. It takes the list of variables on the horizontal axis and the vertical axis. And we can see the correlation coefficients between the specific pairs by looking at the cell, which is the intersection of the two variables. For example, if we want to see the correlation coefficient between V3 and V4, we should look at the intersection of the row of V3 and the column of V4. We can see it is 0.200. We can do the same thing by looking at the intersection of the row of V4 and the column of V3. In a correlation matrix, the diagonal elements are the intersection of the same variable, so all of them display correlation coefficients of 1.000, a perfect correlation. A heat map is a graphical representation of a correlation matrix. It represents the correlation between variables using colors instead of numbers. Usually, the darker the color is, the stronger the correlation is. Besides, to discern the valence of correlation, positive correlation and negative correlations are represented by different colors. Correlation analysis is a simple method to describe the relationship between two variables. However, it often generates misleading results. In many cases, such misleading results are caused by a problem called spurious correlation. Let's look at the scatter plot. The x-axis represents the ice cream consumption per capita in a city, and the y-axis represents the number of heat stroke cases. As we can see, as the ice cream consumption grows, the number of heat stroke cases increases. Can we conclude that ice cream consumption increases heat stroke patients? The answer is no. As you know, correlation does not mean causation. So, we cannot conclude that the ice cream consumption is the cause and heat stroke is the effect. However, in this case, more serious problem is spurious correlation. A spurious correlation refers to a positive or negative relationship between two variables that appears a cause and effect relationship, but it is not. In such a relationship, it appears that one variable causes another, or vice versa. However, in a spurious correlation, the relationship between two variables is caused by a third factor not included in the analysis. Even if we find a correlation between x and y, we cannot immediately conclude that x causes y or y causes x. When a third factor z causes x and y, the correlation between x and y is sometimes meaningless. Both x and y may be just results of z. In such cases, if we are interested in a causal relationship, we need to focus on the third factor, z, rather than the relationship between x and y. So, in the example above, we found a highly positive correlation between ice cream consumption and the number of heat stroke cases. However, both of them may be caused by high temperature. Thank you for watching. Please thumbs up and subscribe to my channel.